So I'm actually working on a longer video about general relativity on YouTube, but I quickly want to share about how fascinating it is that even after more than 100 years that Albert Einstein predicted that gravitational waves exist, we've come so far. We've built so many institutions. We have so many scientists all over the world working on gravitational waves and using them to understand our universe. Because for the longest time in astronomy, we depend on electromagnetic waves, light, to see these structures out in the universe. The problem is that although electromagnetic radiation is really useful, if we've come up with so many images about different structures out in the universe, the thing is that when light propagates, the intensity that we actually get from this light is decreased by the distance squared. So unlike gravitational waves, it decreases a bit, but not as intensely as electromagnetic waves. So this is really useful. But how do we even know that these gravitational waves are real? How can we set up these institutions, these long laser systems, when we can't really see them, and they're also pretty hard to detect because gravity by itself is already a weak force. Is it a force? So Einstein saw the world differently. Space-time is just nothing, even though it also is nothing, but it's also something that can curve. It's something that can have a curvature based on the amount of matter and energy present in this amount of space, and that's what the Einstein field equations are. So the thing is that, for example, you would have two massive objects, two black holes that are interacting with each other, rotating around each other, fighting or whatever. This interaction actually causes changes in the curvature of space-time around these black holes, and that change in the curvature we can relate with gravitational waves. And although these gravitational waves are really hard to detect, it is possible. So what happens is that we have a laser that is divided into two parts, and we bounce those lasers back using a mirror, and once they meet, they're supposed to recombine and form an image. But when a gravitational wave passes by, this interaction between the lasers could change, and the image that we get is now different. It's slightly darker, slightly brighter, things like that. So those changes in the lasers coming in and coming out, that we can quantify and we can relate to gravitational waves. That's really fucking cool, because for things like black holes very far from us, we can see what's going on. We can understand, like, hey, there are these black holes, rotating around each other, and they turn into one big black hole. This is something that we can now detect, and that's hard to do with electromagnetic radiation because black holes, they're black. Okay, we can't see anything. And it's just so fucking cool because Einstein thought of the universe as being made up of space-time that you can curve based on matter and energy being present. And this kind of curvature we can relate to another quantity, gravitational waves, and this quantity we can use to study the universe, especially at a point, moments after the Big Bang, where at one point everything is really opaque and it's hard for electromagnetic radiation to pass. So it's hard to see what's going on at this point in time. But with gravitational waves, you can use this to maybe look at what's happening at that one point where we were literally blind.